Hello, and welcome to Exponential and Logarithmic Models. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas El Paso and an assistant professor at Doña Ana Community College. This particular lecture is for Math 1508, Pre-Calculus at UTEP. Chapter 3, Exponential and Logarithmic Functions, comes to us from Larson's Pre-Calculus 10th edition. Section 3.5, Exponential and Logarithmic Models. So there are some common modeling equations. Exponential growth and decay we see quite frequently, the only difference being whether the exponent is negative for decay or positive for growth. In either case, b, the growth or decay constant, will be considered a positive value. We have logarithmic models, y equals a plus b natural log of x, or y equals a plus b log of x. The human memory model, some population models follow these. Continuous compounding interest, a equals p e to the rt, and the compound interest formula, a equals p times 1 plus r over n to the power of nt. I like to emphasize the fact that your parentheses should be around the exponent, unless you have a calculator that has the display exactly like this. If it just gives you a caret, that little up arrow, then make sure you put parentheses around your exponent. Anytime something's going on in the exponent, parentheses will help your calculator keep it straight. Alright, so let's determine the principal P that must be invested at 5% compounded monthly so that $500,000 will be available for retirement in 10 years. Alright, as soon as I see compounded monthly, I think of the formula a equals p times 1 plus r over n to the nt, and you can see here I didn't put in the parentheses. That's alright. Determine the principal p, so I'm going to look for p. P is going to be a variable. At 5%, my interest rate always is a decimal, 0.05. Compounded monthly, monthly happens 12 times a year, so n equals 12. So that $500,000 will be available. So in the future, $500,000 in place of a in 10 years, so my t value is 10. Notice, with the parentheses around the exponent, I can make sure this whole value is being raised to the 120 power. If I take care of my parentheses, 1 plus 0.05 over 12, I get 1.0041, and then a repeating 6, going old school here with the bar over the 6, to the power of 120. And I don't find that. I don't find that on my calculator and then just use a decimal approximation. I leave the whole thing. To get p by itself, I'm going to take 500,000 and divide it by this expression. Of course, I don't have a 6 repeat. I don't have a button for repeating on my calculator, so I'd enter in quite a few 6s just to make sure my answer is more exact. Or I would just take this answer that was still on my calculator previously in order to put it in. At either rate, as you divide, you'll find that you need $303,580.52 so that you'll have $500,000 in 10 years. If I had that kind of money, I probably wouldn't put it away for 10 years. I would probably use it. But that's just me. Determine the time necessary for $1,000 to double if it is invested. Looks like we have an unnecessary word here. If it's invested at 6.5% compounded annually. Well, to double means my future will be 2,000. Initially 1,000. 1 plus interest rate over annually, n equals 1. I want to find my t value. But remember, I'm going to isolate the exponential part, so I'm going to divide both sides by 1,000. I get 2 equals 1.065 to the t. And once I have the exponential isolated, t is the power. I put on 1.065 to get 2. And if you told someone, hey, why don't you put this in the bank account for log base 1.065 of 2, they would probably look at you strange. Your banker would too. So just tell them 11 years. It's one of these times where math answer, awesome. But real people, understandable answer, way better. If the same problem is now compounded monthly, the only thing that changes is the annual becomes monthly. I'm still going to divide by 1,000 in order to isolate the exponential part. This exponential part kind of looks ugly to the 12t, so 12t is the power to which I raise 1.00541 repeating 6s to get 2. Divide both sides by 12, and it turns out to be 10.69 years. But if we have something like daily, I'm not even going to bother with this decimal. I'm going to divide both sides by 1,000 and I'll get 2 because it doubles. There's a reason. 2 equals 1 plus 0.065 over 365 to the power of 365t. I'm going to leave that number. My calculator can handle it. I can handle it, I guess. Let's see. 365t equals the log base, base of the exponential, base of the log, 1 plus 0.065 over 365 to get 2, to double. And I enter this into my calculator. Absolutely. My calculator can handle that. My brain cannot handle that. But my calculator can. And I'll find out that this is 10.66 years. So from annually 11 years to monthly 10.69 years to daily 10.66 years, you're still going to have to wait a while for that $1,000 to double. Let's talk about some carbon-14. Carbon-14 decays exponentially with a half-life of 5,715 years. Find how much remains from a 6.5 gram sample after 1,000 years. So I'm looking at decays exponentially. And I go and I find my equation, y equals ae to the negative bx, where a is the initial amount, b is the decay constant, and x is time. And then I move on, and I see the half-life of 5715 years, and I ask myself, what's half-life again? Half-life is the amount of time for half of the substance to decay. And then I think about, alright, how are we going to do this? In order to find our decay equation, I need to know A. Well, A is 6.5, it turns out, for this particular example. And I know my x value of 1,000 years, but I don't know B. And remember, E is just a constant, but I have to find B. Let's find B in order to find the future amount, Y, after it's decayed. No matter what we start with our amount, we know that when the time is 5,715 years, half of that amount remains. Whatever the starting amount was, the half-life tells us half remains. But we're going to divide both sides by A, right? We have to isolate this exponential part. And when I divide the left side by A, I just get a half, which I've used decimal form because it takes less space on the page. 0.5 equals e to the negative 5715b. Rewrite it. Negative 5715b is the power to which I raise e, so equals the natural log of a half. Now, to find b, I divide both sides by negative 5715. And my calculator tells me that's 1.213 e to the negative 4. But I know my calculator's giving me engineering notation, and I'm putting it here in scientific notation. But remember that negative 4 number line, negatives are on the left, tells me to move my decimal to the left 4 places. So it was here. 1, 2, 3, 4. My arrow kind of jumped there, but trust me, there's 4. I'm going to use this as my b value. That's a pretty tiny number. That's pretty good for accuracy. Now that I know b, I'm given 1,000 years. I'm given a 6.5 gram sample to start. I can enter this value on my calculator, and I find that after 1,000 years, 5.8 grams still remain out of the 6.5 grams that we started with. Shout out to South Carolina. I've never been here, but we're using this example. The population P in thousands of Horry County, South Carolina. And if I'm pronouncing that incorrectly, I apologize. I'm thinking of an NBA player from 80s and 90s, I think. Robert Horry, that played for Houston. So I'm going with that pronunciation. From 1970 through 2007, it can be modeled by P equals negative 18.5 plus 92.2 e to this exponent, where t represents the year with t equals 0 corresponding to 1970. So we're going to find the populations for various years. We're going to look at the model, and we're going to try to predict when the population of the county reaches 300,000. And we'll talk a little bit about whether or not the model is still valid. So the year 1970 is 0 years since 1970. So I'll put 0 in for t, evaluate, and I get 73.7. Remember, this is in thousands. Our population is in thousands. So this is not 73.7 people in the entire county in 1970. This is 73.7 thousand people in the county in 1970. So that's 73,700. 1980 is 10 years later. 1990, 20 years later. And I evaluate my function at these values of t based on the years after 1970 to find all of my answers. And I can see that in 2007 there were 243,200 people supposedly in Horry County, South Carolina. Now part B. According to the model, when will the population reach 300,000? Now remember, this population model is already given in thousands, and since it's given in thousands, we'll just use the 300. Right? 300,000. 300 thousands equals this thousands. I'm going to add 18.5 to both sides. To isolate the exponential, I'm going to divide both sides by 92.2. Once I have the exponential isolated, I'm going to convert. 0.0282t equals the natural log of my fraction, which leads me to t equals natural log of the fraction divided by 0.0282. Yes, I am starting to wonder if maybe I should check this. Decimal's not there. But I can assure you, that's just clearly a typo. The answer is approximately 43.9597. So about 44 years later, but that doesn't answer the question. When? In 2014, the population should be about 300,000, and I decided to Google it. And it was 297,000 something. And I felt that was close enough to 300,000 that the math is valid. This idea of, do you think this model is still valid? And this is where math, the hard facts of life, and the reality of living meet. Who knows? This is South Carolina. They could have been hit by a hurricane. They could have the biggest industry go out of business and thousands have to move away. Maybe Amazon chooses to put their new headquarters there in Horry County, South Carolina, and they have a boom of population. So this doesn't account for natural disasters and economic hardships or economic flourishing. These models are fantastic within limits. To have it valid 50, 60, 70 years from now, it's probably not a good idea to rely. We should check new data and adjust our model as time goes on. Alright. Pretty sure this is the last example. Here we go. The number of bacteria in a culture is increasing according to the law of exponential growth. As soon as I see exponential growth, I know that I need to write down the equation for exponential growth. Y equals AE to the BX. After 3 hours, there are 100 bacteria. And after 5 hours, there are 400 bacteria. How many bacteria will there be after 6 hours? Alright, so we don't know the initial amount or how quickly they grow. The growth rate B. We must see what we can do with the two given values. 3 hours, 100 bacteria. 5 hours, 400 bacteria. Hold on. We're going to do some algebra here. So after 3 hours, 100 bacteria gives the equation 100 equals AEB to the 3, right? Time is our x, y is our output. We have no idea the initial amount or the growth rate. I can rewrite this as 100 AE to the 3b, and I'm going to refer to this as the blue equation. In 5 hours, 400 bacteria gives me a green equation. 400 equals AE to the 5b for the same reason. Now remember, it's the same model that gives us 3 hours, 100 bacteria, 5 hours, 400 bacteria. Same model, so same A, same B. Which means I can solve my blue equation for A, 100 over E to the 3b equals A, and what we're going to do is substitute that in to the green equation. So let's do just that. If I put 100 over E to the 3b in place of A in my green equation, I'll have 400 equals 100 over E to the 3b times E to the 5b. Now I can combine these. Notice this equation has only B, so I can solve for my B value. And how do I do that? Well, if I'm dividing two things with the same base, I subtract their exponents. So I'll have 400 equals 100 E to the 2b. Divide both sides by 100. 4 equals E to the 2b. We can rewrite this as 2b equals the natural log of 4. So b equals the natural log of 4 over 2. And I can find that decimal on my calculator. We'll call it to 4 decimal places, 0.6931. Fantastic, we found b. We found the green b, but remember, it's the same as the blue b. And since I do have my b value, I can put it back into this equation where we solve for a. 100 over e to the 3b, substituting my value, equals a. And this is approximately 12.5. All right. But we're not finished yet. Right? A equals 12.5, B equals 0.6931, but I want to know how many bacteria after 6 hours. With our formula y equals AE to the BX, at 6 hours we have y equals 12.5, e to the 0.6931 times 6, and we end up with 799.8. But these are bacteria. Let's not get into is it living or is it not with the 0.8. Let's just round that and call it 800 bacteria after 6 hours. There we go. I guess if we really think about it, 3 hours we double at 4 hours and we get 200 bacteria. After 5 hours it doubles and gets 400 bacteria. So it doubles again after 6 hours to give us 800. We did it the hard way. The hard way always works. But don't neglect the common sense. Common sense is very helpful when it comes to math. That's it for this lecture. Thanks for listening.